Hi, welcome to this video on why pi is irrational. In this video, we're going to construct a proof of why pi is irrational using techniques that you would have seen before the age of 18. I've put a brief description on what we're going to do in this proof. So we're first going to prove that if pi squared is irrational, then pi must be irrational. The reason for this is because the step 2, we're going to prove that pi squared is irrational. So if we know that pi squared is irrational, it would be helpful if that implied that pi is also irrational, which it does, and we're going to see a proof for that. And then we're going to move on to step 2. As always with an irrationality proof, we're going to assume the opposite. We're then going to define a function. This function is the hard thing to sort of pull out of the hat, but unlike in other proofs of pi being irrational, this function is not too big, it's not too disgusting. We're then going to prove that whenever n is an integer, an is going to also be an integer. Where we're going to get our contradiction from is when n gets very big, we're going to show that this function is between 0 and 1. So it's not equal to 0, but it's bigger than 0. It's not equal to 1, but it's less than 1. But there's no integers between 0 and 1, so we get this contradiction. And that's going to be the whole idea of this proof. Now, I've kind of put like the hints on what we're going to do, so you may choose to try it yourself. For the step 1, we're going to use a contrapositive proof. For the next part, we're going to use contradiction, and then we're going to use induction. For as n gets big, we're going to create an upper bound and a lower bound for our integral, and we're going to show that this approaches 0 on both sides, which then, by squeeze theorem, we can get to that conclusion I just talked about. So step 1, prove pi squared is irrational implies that pi is irrational. So for this, we're going to use a contrapositive. So if pi squared is irrational, then there are two cases for pi, as always. Case 1, pi is rational. So if pi is rational, we can say that pi equals p over q, with the usual understanding that p is an integer, q is an integer, their greatest common divisor is 1, and both of them are non-zero, unless we're dealing with something that's non-zero. The other case, and this is the only other case, pi is irrational. You can either be rational or irrational. There is no other case. Now, if pi is rational, then pi squared equals p squared over q squared. But p squared is an integer, q squared is an integer, and their greatest common divisor must be 1. So pi squared must also be rational. So case 1 could not possibly imply the second thing. There is no way we could have case 1 and this thing in the red to also be true. So by that, we find that pi must be irrational. And this sets us up for step 2. Okay, so let's crack on with step 2. So we're going to start off with sort of the basic, every single proof by contradiction, irrationality proof. So pi squared is equal to p over q. So we're assuming it's rational, where p and q are integers, they have no common divisor. So you can't simplify this fraction. Next, we're going to introduce our function an, like so. And what we're going to do is we're going to prove that it's an integer for all n greater than or equal to 0. So first of all, let's do the base cases. So base case. Now I'm actually going to do 2 base cases, and you're going to see why later on. But we haven't actually done this before with proof by induction, if you've looked at my video series on this. But I'll explain that briefly later when we have a look at it, which is quite beautifully 2. So clearly works for n equals 0. So what about for n equals 1? Well, for n equals 1, we have a1, leaving us with 4q, and now q is an integer, so we get it true for a0 and a1. So quite a lot of computation, but the main thing is we've shown that A0 and A1 are both integers. That's the main thing, because Q, by definition, as we've assumed up here, was an integer. Next, let's have a look at assuming true. And again, this is a bit contrary to what we've seen before. We're going to assume true for n equals k and k plus 1, i.e. ak and ak plus 1 are integers. Nice. So let's go ahead and have a look at this. So we're going to consider n equals k plus 2, i.e. ak plus 2, which is equal to q ak plus 1 minus, well, this is going to be q squared pi squared ak plus, well, now we're going to have 4q k plus 1 ak plus 1, which leaves us with 4q k plus 6q ak plus 1. And remember, pi squared at the start, if we go back up all this way, we've done so much work here, pi squared equals p over q. So what we're really left with here is p times q ak. So we've got an integer. An integer. By assumption, an integer. And again by assumption, an integer. So this is an integer. So we've done mathematical induction. We've found that ak plus 2 is simply an integer times an integer minus an integer times an integer. So it itself is an integer. So by mathematical induction, an is an integer for all n. Really, we're talking about the natural numbers, positive n. We haven't considered negative n. So we now need to form our contradiction, and then we're pretty much there. So if we have a look at our an, we want to find an approximation. So an is equal to qtn over n factorial times integral between 0 and pi of x tn pi minus x tn sine x dx. So let's have a look at approximating this. Well, first of all, on this bound, we have that sine x is between 0 and 1. We have that x, well, what's x between? Well, x is between 0 and pi. And likewise, pi minus x is as well between 0 and pi. Which means we can approximate this. This is equal to qt, well, less than and equal to qtn over n factorial times the integral between 0 and pi of, well, this is going to be pi to the n times pi to the n times 1 dx. This is a big approximation here, which is going to give us qtn n factorial pi to the 2n plus 1. But this goes to 0 as n goes to infinity. Factorials beat exponentials. So this goes to 0 as n goes to infinity. What about on our lower bound? Well, the lower bound is that this is bigger than or equal to 0. All of the terms are positive. So by the squeeze theorem, we get an goes to 0, as n goes to infinity. So for large n, we have an is between 0 and 1, i.e. an is not an integer. And that's it. That's our contradiction. So we get that pi squared is irrational. And well, if we look back at the top, pi squared is irrational implies that pi is irrational. And so we are done.